Okay, well, welcome to our project. This is Maria Esteva and Weija Hugh. We both work at the Texas Advanced Computing Center at the University of Texas at Austin, and we represent a larger interdisciplinary team that works under the funding and umbrella of the Good Systems Initiative at UT Austin. In this study of spoken audio processing using machine learning for libraries, archives, and museums. Next, please. So audio recordings are critical to scientific and cultural inquiries, and providing prompt and accurate access is an imperative for cultural and academic institutions. From performances and oral histories in literary and historical studies to scientific sound recordings, the use of audio recording is increasingly exponentially in scope and scale in libraries, archives, and museums. Meanwhile, LAM professionals, that's how we are going to synthesize libraries, museums, and archives from now on, are often under-equipped to manage the demands of describing massive audio collections using the manual methods that we all know about. Machine learning applications to assist LAM collections management has resulted in both admirers and skeptics. Deploying automation for collections processing could support LAM professionals charged with preserving and providing access to these materials. For example, machine learning tools can be used to generate metadata with which users can easily search for items within a collection and that LAM professionals might otherwise have to assign manually. While these solutions might improve and accelerate processing, there's a steep road ahead towards researching, developing, and maintaining such methods. As LAM professionals work towards adopting automation, it is critical to question the role and functionality of machine learning in relation to the unique requirements, best practices, and professional training in this context and the interdisciplinary work that it entails. And this is our motivation. So we went to, to study to formulate these evolving questions. And at the beginning of our project, we set our goals and research questions. And our goals were very practical. We wanted to automatically generate metadata. And our first questions were geared towards finding practical solutions. We assumed that we would work with perfect automatic transcriptions and obtain the right amount of labels that we wanted. But as the project progressed, we had the opportunity to observe more in depth the manual practices that we wanted to emulate, the possibilities and limitations of the transcriptions, the different research approaches, qualitative versus qualitative, practical and deductive on the one hand, and experimental and inductive on the other. And all of these made us redefine our questions, which evolved over time. And you can see in the alignment that there are parallels between the more LAM-oriented and computer science questions, and that our different perspectives align as paths towards finding answers that will need continuous work. To produce all of this, for this study, we used the Historias collection, which proved to be a very compelling and challenging case. This is, you all know about this StoryCorps from the public radio. The Historias is in particular a collection that focuses on the Latino community, on the Latino experience. And we needed really to understand the provenance of this collection, how it was collected, how it was produced. And for that, we captured interviews with the librarians that generate this collection, with the archivists that archive this collection. And so this is interviews between two participants with the aid of a facilitator. So you listen to more than one voice. This is in English with sparkles of Spanish. We were able to get 815 audio files of up to 1 hour. And the metadata for each interview was created by the facilitators on the spot, meaning they basically describe, these facilitators describe the collections and do the metadata as soon as or during the recording process. They always try to describe the collection in the audience in general. That's what they're trained to do, to describe the general content of each audio collection. Think about each as a record, as an archival record with many subjects within. And they choose from a controlled set of fixed subjects. So we focused on that. Then they can put other keywords, but those are very varied. They do not necessarily need to be from a controlled vocabulary. So we really focused on the fixed subjects. And here, Weijia will talk more about the design of the methodology.
So here is the overview of our processing flow and the major components in the system. We start with the audio data, and which comes with the fixed subjects. For the audio data, we go through the ASR process, which generates the speech transcript. Then we combine with the fixed subjects to generating a text classification models based on the transcripts. Once the model is generated, we also have a component allow user access, where user can read, listen to the audio data, go through the ASR and generating transcripts, and then get the prediction, where user may also do the feedback. So the top part is happening in the HPC cluster, while the bottom part can be installed through the web applications running on the virtual machines. So for the speech to text, the general process is we start with the audio file, then we generating audio features from the audio file. Those audio features are turned into acoustic models. The acoustic model will be passed into the decoder, where the decoder also has language models to together they translate the input audio file into text transcripts. In this project, we use the two ASR functions. One is a open source code called DeepSpeech. It has a good performance result reported from literatures, but it has a very limited acoustic model and language model to support. For comparisons, we also running some of transcripts through the Google Speech to Text services. This is a commercial web services. It comes with a cost about 2 cents per minute, but they support more complex acoustic models and multilingual language model support as well. Finally, we also select another subset of the data and ask professional transcription services at UT Libraries to manually transcribe those records. So altogether, we have 815 transcripts, and we can run all of them through the open source DeepSpeech implementations. We use the pre-trained models to get the transcripts. For the Google Speech to Text, and we use the free credits, and which covers about 300 transcripts. There are some post-NLP processings comes with the Google Speech to Text, so the results looks much better than the one coming from DeepSpeech. And finally, we have 81 transcripts that we ask the professional to transcribe them. So the results for each of those services can be seen on the right. As you can see, for the human transcribed results, there are also added information like sentence mark and the speaker's ID. For the auto-transcribed result, there's no any of additional annotations. And the Google transcribed result reads better than the DeepSpeech, where you can clearly see some of the misspelling words are being auto-corrected as well. To further quantify the qualities of different transcribed services, we calculate the word error rate. We use human transcribed result as a gold standard, and then we align other transcripts from same audio to the human transcribed results. So the word error rate is calculated as a percentage of number of the total IDs needed to transform the auto-transcribed result into human transcribed results divided by the total length of the reference sequence. So on the right, the graph shows how Google Transcribe Services and the DeepSpeech Transcribe performs. Overall, they are very similar. As you can see, the two curves are almost in the exact shape, but the Google services generally runs better with a lower error rate for almost every single files we have. So what it does says is one is a Google Speech Transcribe does has a better model that can give us better result. On the other hand, it does indicating the variability of the quality of the recording. As you can see, some of recording is really hard for both. method to correctly transcribe, and some is much easier. Once we have the transcripts, the next step is to generating the model that we can predict the labels from those transcripts. The general process for this is we start with the transcripts, and we go through the standard NLP processing to extract the language features. Then we turn that into vector representation together with the class labels generated from the fixed subjects. We can build the classification models. During this process, and there are a lot of variations. For example, the different vector representation models we can use different way to define the class labels and different learning algorithms. So we tried some combinations of those. So first, we need to talk about the label selections. There are about 500 different fixed subjects are being used over these 800 data collections. However, as you can see here, only 26 labels appeared more than 200 times among the 815 recordings. So based on the statistics, we decide to focus in on the top 20 most frequent fixed subjects as a base for our training models, and which means we ignore the labels with the less frequency of appearance. And also, we need to decide what to predict, because not every labels in the top 20 will be appeared in the every recording. In fact, the number of labels per interviews varies greatly. As the figure show here, only 85% interviews has 3 or more labels or in that top 20 labels. And 75% interviews has 5 or more labels from that top 20 subjects. So our initial inference are focusing on predicting the 3 labels. So we use the supervised learning method and we test the different model combinations. Here we report 3 models. They are from 2 larger categories. One is we call the single class models. Those models can predict 1 label at a time. So for top 3 labels, we internally has 3 labels, 3 models for that. So, and we use 2 different algorithms. One is a random forest algorithm, and the other one is called a deep learning based algorithm through the BERT. The other category is a multi-class model. So in contrast to single class model, where we do 1 prediction at a time, we can predict all labels at the same time. We call it DL-MATI models, and we use BERT to build these models as well. So BERT is a deep learning based NLP libraries. It has been used very popular and very successfully in many applications. So the other things is on the testing side. So typically the standard testing is to using 80% of the training available data as a training, and use the rest of 20% for the testings. So we did that, and we also did, because we have 3 different transcripts sites, and we also did what we call the deep speech testing, where the test data set are from 100 deep speech transcripts, regardless what transcript data set they were used for trainings. So here we show the result of top 3 label predictions, the RF model and the DL top N model and DL-MATI models. Because of the this is for top 3 label prediction, where the RF model and DL top N model was specifically built for that. So the result appears to be slightly better than DL-MATI, but DL-MATI is more flexible. But in general, and we consider they are on a similar level of the performance. So this slide shows more about DL-MATI models and how the more than 3 label prediction is. So on the left is a table where you can see the 0.66 are the same average accuracy we showed in the previous slide. The previous slides and all the results are trained and tested with the deep speech transcripts. For DL-MATI model here, you can see if we use Google Speech transcripts or human transcripts, we significantly improve accuracies. What is more interesting is that Google Speech actually has much better results than human transcripts. This is partly due to we have much fewer set of the human transcripts available. On the right is a curve that shows how the top N label prediction performs. So as we get more labels out of the outputs, and we can see the average accuracy eventually drops. So here, the top 3 labels shows here are the 3 data points is highlighting here. So the top curve is using the Google services, and then the blue curve is from human transcript services. So they were trained and tested on their corresponding transcripts. For the bottom 3 curves, they are built using Google Deep Speech and the human transcripts respectively, but they all tested on exactly same testing data set. So what this one shows is the quality of transcripts does has a significant impact on when we do the inference. So those are the computational analysis of that. So to enable user evaluation and access, we also build a web application. The web application leveraged another project called IDOS. The IDOS is a reconfigurable on-demand web application framework for interacting with hypercomputing resources. So it's easier to develop and to configure. That allows us to easily define the web application interface with the data curator together. So next, I will turn back to Maria to go over quickly about the web access interface here.
So a user can either run the entire workflow from the audio to the labels all together, or can take the tasks one at a time to really evaluate and see what is being done. They can listen to the audio, they can edit the script, they can share that script with other professionals that may need the same type of workflow. They can also read the results of the different transcription methods. And then when they get the labels, they can compare the labels with the ground truth labels, meaning the labels that were selected by the librarians to begin with, compare the results, see what the matches were and what the matches are between one and the other, what labels were recovered, and also provide feedback to the system. So this is a work in progress, but it really does transparency and reproducibility, which are library, which are values that we cherish. So if you see here, one of the things that happened is that librarians really, or curators, we really need to see the results. It's not just numbers that tells us this, this has a certain percentage of accuracy, this has a certain percentage of accuracy, but we really wanted to verify that the descriptions were meaningful to a user. So our qualitative evaluation included a sample of audio files whose labels were predicted using DL multimodal with data from Deep Speech, Google Speech, to text and human transcriptions. Here are the results of one of those audio files. And one of our surprises was that across all the interviews, the labels predicted from the Deep Speech data were all the same. So we really needed to do an expert assessment. We really needed to understand whether these labels that were produced by librarians, these top labels produced by librarians or by facilitators or archivists, were really a model, were really our ground truth. So when we were initially looking, and this just talks about how these quantitative assessments that Weija was doing to understand the metadata that was going to use to train the machine learning models, we could also use to assess our practices. So when we looked at the top 20 ranked labels, we were noticing how repetitive they were, how lack of diversity they had. And so learning about how metadata was assigned to Historias by the facilitators really was a clue. We learned that, there was not a uniform, there was a uniform criteria, but different facilitators described each of these or many of these audio, so there was not a consistency. So this quantitative analysis helped us understand the lack of diversity and content representation and the coverage and inconsistency. So we did 2 simple exercises to understand the consistency in applying metadata, and we found we did it, within the team, and we realized that catalogers selecting metadata for a same content can differ in their criteria, even if you have you know, 2 catalogers listening to the same content, or 3, in this case we were 4 catalogers listening to the same content, we differed in the criteria. We all picked from a top 50 labels, we picked different labels, or many different labels. Also, we talked about, we did another exercise to understand the diversity of subjects for collection representation. And what we realize is that when we curate these subjects and we agree upon these subjects, what subjects to apply to a corpus of data, it's a step forward towards a common meaning. So there's also a balance that librarians have when selecting subject headings, that has to do between going too general or too deep into a description. And this is very difficult with archival records, because the archival records have many subjects. So when you are told to describe the subject in general, there's always this tension between how to describe it in general and how to describe its components. So this goes about, is it possible to use the metadata that we have in libraries as is, or should we design metadata for machine learning? Should we curate control vocabularies? Can we use hierarchical relations between top schema and narrower terms, and do a more design approach to get the real labels that we are going to need to train machine learning models that are going to be more satisfactory? Can we improve subject distribution, implementing beginning, middle, and end subject assignment approach, which is something that the librarians from the StoryCorps wanted to do, but maybe could not really achieve? And always interlace your strategies, your design, your metadata design with machine learning testing. So this is also something we learn. We need to be more experimental as professionals. The conclusions are that in terms of the machine learning for description or for labels, we can use machine learning to go directly from audio to labels without focusing too much on the quality of the transcriptions, while keep exploring possibilities to improve transcription. We don't want to discard deep speech at all. It's an open source tool. It can be improved. It's open source. We can work on it. We use it as is, but it can be worked on it and improved to get the results that you want to achieve. We need to work more on curation of metadata for training, or creating metadata for machine learning, and maybe we can start working on that towards consistency and diversity of representation, and so that we can use it in understanding what the machine learning methods are. We can understand how to apply and create metadata as a ground truth or for models. But we also, and now we are working on unsupervised subject extraction. So this means that we are not using produced metadata for our models, but we will extract the subjects out. It's going to be a different product, but we are now, this is what we are testing. In terms of machine learning adoption and transparency, it's great. I think we keep working on IDLES to improve explanations, to improve the interfaces, so that we can manage and evaluate machine learning workflows. We can share code and infrastructure resources across institutions. IDLES is implemented in a supercomputing center. It can be used by various institutions at a time. It can be used by different projects, and the projects can share components or workflows, and that is it's working towards that ideal. And of course, we need to test IDLES across many LAMs. And of course, the new responsibilities and possibilities. So learning that these qualitative methods can improve quantitative methods and vice versa. So we need both. And of course, continuing with interdisciplinary work. Thank you very much. And we look forward to your questions in the interactive session.